morning to one and all present here. It gives me a great pleasure in welcoming Dr.R.AnandaNatarajan sir, professor from Puducherry Engineering College, Puducherry Technical University. Dr. AnandaNatarajan sir has a total experience of 20 years in industries and academic. He has published more than 14 journals in national and international level, attended national conferences in 12 numbers, and has attended more than 6 international conferences. His membership in various professional societies, like a member in Instrumentation System Automation ISA, fellow in Institution of Engineers, life member in ISTE, life member in System Society of India, life member in Computer Society of India, list of and also he has funded many projects like research projects like AICT sponsored project for the implementation of smart machine vision module with the self-configurable intelligence, and AICT sponsored project pollution-free battery operated electric vehicles, and DSTE Puducherry sponsored project study on the levels of pesticide residues in agricultural products available in Puducherry region. He is also an advisory committee in a number of professional bodies, and he is a technical consultant for process automation, technical expert in hologram implementation committee in government of Puducherry, Rajasthan, and Madhya Pradesh. And his profile is very long, and due to time constraint and limited this professor with your permission. And I request Professor Dr. AnandaNatarajan sir to hand out to welcome to this session, and it is a very ideal person for this DCS for handling DCS as an automation tool, evaluation and architecture topic. I request Professor to continue with the session.
Thank you. Thank you for your introduction. Very good morning to all. Today we are going to see introduction. Introduction to DCS. DCS as an automation tool, evolution and architecture that we are going to see. But of course, it is an introductory lecture on DCS. My idea is you should understand what is DCS, how it works, so that you can enrich your knowledge on DCS further. That is my idea. First of all, I'd like to thank all my teachers, particularly Professor S.P. Natarajan, former professor and HOD E&I University, for guiding me for my UG. He taught me all subjects in the AMIE. I'd like to thank him. Professor M. Chidambaram was my guide for my PhD in process control. He was former professor in IIT Madras and the former director in NIT Trichy. Presently, he is professor NIT Warangal. Professor T. Ratnavel taught me software C, particularly C. He said it will exist for another 20 years, and he taught me in 1990. But now 30 years gone, still it is ruling the software domain. Then I would like to thank the late Professor M.Z. Vaidilingam for guiding me for my MTech thesis, as well as he taught me control system and process control. Thank you, teachers. Not only this in the list, many professors gave me a lot of knowledge. Thank you, Ananda. I am author of the following books: Biomedical Instrumentation Measurement. It is published by PHI, New Delhi, and Digital Design. That is also published by PHI, New Delhi. The Digital Design book consists of a lot of questions from GATE. Those who are preparing for GATE it will be very much useful. Those who are working on VLSI can also having programs in that book. I am co-authored the following books with Professor Ramesh Babu. Control System Engineering is published by Sci-Tech Publications. Then Signals and System, that is also published by Sci-Tech Publication. The 5th edition of these two books came in 2017. And we wrote another book, Basic Electrical and Electronics Engineering. That is also published by Sci-Tech. Now let us come to the distributed control system. It is nothing but a collection of hardware and the instrumentation necessary for implementing the control system. So DCS, the definition for DCS is collection of hardware. Collection of hardware connected to a network, connected to the network bus for implementing control system. That is the definition for distributed control system. It provides an infrastructure for implementing advanced control algorithms. That is the advantage. One of the main advantages that any advanced control system can be implemented by using DCS. That is another advantage. So it is nothing but collection of hardware under a bus. If you take the history of control hardware, before invention of electrical signal control came into picture. The earlier the signal is transmitted by using pneumatic signals. The pressure signal, the signals transmitted pneumatically are slow responding and susceptible to interference. So any interference, it will affect because of interference. But it is 3 to 15 PSI is used to transmit signals like electronic signal. The calculation is based on mechanical computation devices. They must be relatively simple and tend to wear out quickly. So and the devices used here wear out quickly because of wear and tear. Then analog signal came into picture, 420 milliamps. Analog signals are also susceptible to noise. But if you use current signal, there is somewhat better resistance to noise. The signal quality degrades over long transmission line. The transmission line is very long. The signal quality degrades. The type of computations possible with electronic analog devices still exist. These are the then the second phase is analog signal, that is used in the control. The third improvement, the third phase is digital signals are used. This far less sensitive to noise. It is highly immune to noise. It is highly immune to. That is the very good advantage of digital signal. So we are sitting at home and we are looking. We are seeing that live commentary without any noise. Without any noise. These are all possible because of digital signals. Because of digital signals, that is highly immune to noise. Highly immune to noise. For this, the computation of these signals can be done through digital computers. So this is the evolution of signals used in control system. First, they are used in pneumatic signals, then analog signals 4 to 20 milliamps, then it is digital signals. So once a digital signal is used, then DCS is the one. DCS is the one. Digital computers are more flexible because they are programmable and no limitation to complexity of computation. whatever may be the complexity. Earlier, what we will do is we will design the controller mathematically, then it will be implemented using analog circuits. So there are limitations because of it has saturation and cutoff in every device. There is a limitation for that analog devices. Implementation of algorithm using analog devices. But if it is using digital computers, if you use any mathematical expression can be calculated, then it can be converted into electrical signal. It can be numerically evaluated controller output, then it can be converted into signal. That's why any complex algorithm, whatever may be the complexity, whatever may be the level of complexity, it can be implemented in digital computers. So once a digital signal can be used in control, then digital systems digital systems are replacing the controllers, because any complex algorithm can be easily computed. Another advantage of digital systems is more precise. Whatever the output you are calculating means if the device gives the exact algorithm output is given by that system. That is the advantage. Cost less, digital system is less cost nowadays. We are having a powerful computing device in our hand as a mobile. So very less cost to install and maintain. Digital data in electronic files can be printed out, displayed in color terminals, and stored in highly compressed. Whatever the amount of data, earlier we used to record these data on a tape, but it's very difficult to compress. But nowadays, any data can be compressed and stored in a very small area. These are the advantages of digital system. Now, if you turn our attention towards control, then this is direct digital control. If we implement, we have seen what are the advantages of computers in control. So far we have seen. So if you use a computer as a controlling device, so any complex algorithm can be implemented. Any number of cascade. Here it is two loops are there. One loop controls the level in this tank. The level in this tank. This is the tank in which this level has to be maintained. For that, a level transmitter is there. Level transmitter means it measures the actual level here, and it transmits as a signal to this computer. And another one is the temperature inside. The temperature of this liquid has to be maintained constant. That's why another sensor is there. The sensor transmits the actual temperature transmitter transmits the signal to the system. So this is called in control system process control. It is called a process variable. This is process variable 2. This is process variable 2. So once if you want to control, what you have to do is you have to measure that variable. Then only you can control. For example, if I want to drive a car at 60 kilometers per hour means, first I should know what is the present speed. Then only I can control. That's why the process variable is the present variable that is measured. It is compared with the desired value, set point. Set point 1, set point. This is set point for temperature. This is set point for level. It is compared with that. If there is no difference, there is no change in valve opening. There is no change in valve opening. This is the valve, control valve. If you open more flow rate will come here. That's why level will increase. The level will increase. So if you open more, level will increase. If you close, level will decrease. So it will compare set point 2 with set point 2 with the process variable 2, that is level, actual level. If the level is greater than set point 2, then it will close the valve further. If the level is less than set point is higher, it will open the valve more. So it depends upon this error. This system will take necessary action to open this valve or close this valve. Here we are using what is the input signal given here? The input signal given here is analog signal, 4 to 20 milliamps. This is 4 to 20 milliamps. This is another 4 to 20 milliamps. So it cannot be read inside this 420 milliamps. It should be converted into digital signal. That's why an analog to digital converter is there. So this 4 to 20 milliamps is given to the analog to digital converter. So it converts this into analog digital value. So it is compared with the digital value. The computer algorithm is another digital expression, mathematical expression. That algorithm gives how much the valve has to be opened further or how much the valve has to be closed further, so that the level will be maintained equal to set point 2. Set point 2. That is computed here. How much opening? 10% opening, 5% opening, 3% opening, or 3% further close from nominal opening. That it will tell. That is again converted into digital signal to analog signal, digital to analog converter. That converts that signal again come as 4 to 20 milliamps. You notice that here it is entering, the input is entering as 4 to 20 milliamps. The leaving as 4 to, output is leaving as 420 milliamps. Outside world is 420 milliamps, but inside it is digital. Similarly, for temperature, here it measures the present temperature. It compares the present temperature with the set point 1. So set point 1 is compared with the process variable. If any error is there, this thyristor power controller will give more power to this heating coil if temperature falls below the set point 1. If the temperature exceeds that point 1, it will decrease the power. In other words, it decreases the voltage. So thyristor power controller controls the power because power is proportional to VI. So either we can adjust voltage or current to adjust the power and this heat dissipation from this coil. So this is the digital control environment, computer control. We have seen so far is called computer control. Computer control. Why it is called computer control is inside computer it is digital. That's why it is called algorithm is in digital. That's why it is called computer. Any computing device is involved as in the place of controller, then it is called computer control. So here a computing device, a computer is replaced the controller. That's why it is called computer controller. It is called computer controller. Here, two loops are controlled by this computer controller. If you see a conventional controller, how it looks like, a conventional controller will be looking like this. Conventional controller will be looking like this. Set point. So here controller, analog controller. That gives 4 to 20 milliamps. 420 milliamps output that is given to final control element, say valve. In this case, two final control elements. One is valve. It works on pneumatic signal 3 to 15 psi, but here we are getting 4 to 20 milliamps. 420 milliamps is the I to P converts 420 milliamps into 3 to 15 psi. So this valve works for 3 to 15 psi. Similarly, here this thyristor power control directly works on 4 to 20 milliamps. If voltage will be maximum and 20 milliamps, voltage will be minimum for 4 milliamps. So the thyristor power controller will control the power like that. So if you take a conventional controller, how it should be, this is the valve, let us say, this is the valve kind of final control element. So this is the tank. The level is measured here. A sensor is there that measures this is the tank. Then level transmitter that measures. That level transmitter gives 420 milliamps output. Depends upon the level. Level is 0, then 4 milliamps. Level is full 20 milliamps. It is compared with the set point. Set point, say it is 50%. This 420 milliamps corresponds to 0%. 20 milliamps corresponds to 100%. So it compares. The error signal is again 4 to 20 milliamps. So this controller computes based on the error signal in terms of current, output also current. This is called conventional controller. Conventional controller. Here analog controller. Conventional analog controller. Analog controller. It has limitations. So here controller algorithm you cannot change as you wish. Let it be a PID controller. If you want one more control loop, as we have seen in that, you have to put one more controller. There we used computing device itself has 2 controllers. Here you need one more controller. This is controller 1. Another one is controller 2. Controller 2. This final controller, this thyristor power controller, 420 milliamps is given here. TPC, thyristor power controller, gives power, electric power to the heater. Heater and a liquid, and a liquid tank is there, and the heater is there. So the temperature is measured here, temperature transmitter. Again 420 milliamps we are getting, that is compared here with the set point 1. So it gives error signal 4 to 20 milliamps. The controller gives again 420. This is conventional controller, analog controller. You needed 2 controllers, but here if you see that one computer itself doing both loops. If you add one more, the same computer will do the thing. But anyhow, there's limitations, number of channels in ADC and the speed of ADC, sampling period. DAC similarly, how many channels that we heard, depends upon the hardware. Limitations is based on the hardware. Anyhow, so minimum 8 channels we'll have for both ADC and DAC. So this is computer control. Computer control. Here, this is conventional analog controller that we have seen. But what is the drawback with this direct controller? If it is a laboratory system, one system can control this, but this is not sufficient because in a large scale, because this computer fails, the entire plant will fail. Therefore, direct digital controller, this is called direct digital controller. Direct digital controller. So in the direct digital controller, if the computer fails, the entire plant will fail. Therefore, this is the disadvantage of this direct digital controller. The next one is supervisory controller, because the people won't believe the digital controllers. Initially, there will be a resistance. So then they want to give it as a hybrid. So you keep the analog controller as such. You can keep the analog PID controllers as such. For that, the process variable is given to the process variable coming from the transmitter is given to this analog controller. Set point is given by this computer. Set point is given by this computer. Anyhow, it is analog controller, a combination of analog controller. Then what is the purpose of this computer? Computer will supervise. From computer, we can change the set point, that's all. But anyhow, the conventional controller is controls. Here, the process variable 2 is the temperature that comes here. And set point is coming from this DAC. Here it is coming from this DAC here. And the analog controller gives 420 milliamps. 420 milliamps. Here also it gives 420 milliamps. So what is the difference between that computer, direct digital control and supervisory control? It supervises the analog controls. It supervises the analog control. If you want to change any set point, computer will change the set point in the analog computer. So it is analog computers are interfaced with the computer. And we want the data. That's why the process variables are given to the computer, to the ADC, that you can see the values. You cannot, the computer will not control, but the actual control is analog controllers only. But you can see the process variable. The trend can be seen. This is already we have seen. This converts 420 milliamps into 3 to 15 psi. So here again, if you see that whatever may be the system, this analog controller, this or the computer direct digital controller or supervisory controller, whatever may be the system, there is no change in the left hand side. Remains same. The process instruments are same. The only thing is the control room is modified. Control room is modified. The next one is data acquisition system. So here the data acquisition system means SCADA, that supervisory. If you combine supervisory and this, you will get SCADA. Data acquisition system means the data has to be acquired and stored as mandatory. That's why it is very, very important to store data. So using computer will be convenient to store data and acquiring data and storing data. That's why it acquires and stores. That's all. So it is a data acquisition system. In this case, again, analog controller is used. The set point is we are going to change in the analog controllers, and the process variable is directly given to the analog controller. Again, it is almost identical with the previous one, supervisory control. In the supervisory control, set point is given through computer. Here, set point is directly given to analog controllers, but data only recorded. If you combine these two, supervisory control and data acquisition system, then you will get SCADA, supervisory and data acquisition system. That is called SCADA. So you can you can supervise the analog controllers. At the same time, you can acquire the data. That is called SCADA system. This is the next variation. Yes, any data can be, whatever the data acquired can be used for analysis. That is very much possible. Very much possible. So the control room is now it becomes network. Like we are using LAN network. So internet, these are all the networks that we are using for our communications. Like that, industrial networks are there. The industrial networks are used to interface all devices. If you connect all these devices, whatever the devices that we have seen so far, if you connect all these devices through the networking, industrial networking, then it becomes DCS. So you note that again in the left hand side is same. There is no change in process. Process is again same. Same process, same temperature transmitter, same level transmitter. It is given to that ADC. Here it is given to DAC. What is the purpose of this microcontroller based controller? It acquires the data, and it places its data and calculates the control output, places on the network. Similarly, here also the level transmitter gets the process variable 420 milliamps is coming here. That 420 milliamps is converted into digital signal. It calculates the controller output, places in the same network. Earlier, what we have seen is here, for each data, each output, separate wire is there. So the 420 milliamps wire is running. Suppose 100 loops are there, means 100 into 200 wires has to run from the control room to that. It may be about 1 kilometer away control room. 1 kilometer to that plant, you have to run that many wires. Now that the number of wires is reduced to 1. It is a network. So whatever the data, whatever the controller output it calculates, place this on the network. This is also placed on the network. So a single communication link is connected the entire plant. Therefore, wiring becomes simple. The wiring problem is avoided. So cost involved in wiring is avoided. So how this happens, we'll see this this is conventional controller. Conventional controller. Here, one bus is there. Bus means what? Group of wires are called bus. So networking bus, two wires, only two wires. You can see that our internet connection and all. If you see that only two terminals are there. Two terminals like that. This is two wires are there. Sorry, two wires are there. It is a bus, communication bus. Only these two wires. This two wire is running for the entire plant. In the plant, one process is here. Here we have to control level. So a level transmitter is there. Level transmitter is there that measures it. This level transmitter is a digital output. It has digital output. It has a digital output. It has a digital output that places its data on the bus along with its tag number. So let us assume that it has a tag number of 0, 1. So the digital data placed on the bus has a tag number 1. It means process 1, process variable 1 is having a tag number of 1. It is placed here. Another process is here. Another of this tag number is 2. It add the tag number with that process variable and again placed its data on the bus. So bus has two data. Let us assume that like that thousands of data can be placed in the same bus. Here in control room, this is field. This is field. This is field. This is the control room. Control room. Or maybe here, somewhere here. This is also field 1. This is field 2. Or here, one controller is connected here. One controller is connected here. This is controller tag number 3. Tag number 3. It has to control PV1. So it takes the data of PV1 from the bus and calculates the how much value has to be opened. It calculates because we have seen level and temperature controller. In that value has to be opened further, or value has to be closed further means it calculates that value and place this on the bus. Place this on the bus. That's all. The controller is connected to the bus and it is placed its data on the bus. Another controller is connected here. Another controller is connected here. That is, it has a tag number of 4. It is looking for PV2. And so it wants to control the temperature of this process. So it takes the data of this process, calculates how much its data on the bus. That's all. So here, one digital final control element is there. This is a thyristor power controller. It is digital enabled. So whatever the digital data, it takes that and calculates the how much power it requires. So this is the heater. That heater is connected to this thyristor power controller. So it takes the data. Its tag number is 5. Tag number is 5. Another smart valve is there. Smart valve is there. Smart valve is there. That is tag number 6. Tag number 6. It takes the data sent by this controller 1. This is controller 2. Controller 1, tag number 3 places some data on the bus that is taken by this smart valve and it adjusts the inflow rate to this tank. Inflow rate to this tank. So this is distributed system. Here, some computers are in control room. Some computers are connected. You can monitor the changes here. The same data sent by tag number 1, tag number 2, and tag number 3, 4, 5. Everything can be seen from here. any number of modules can be connected to this network and can be seen. So this has a tag number of 7, 8. It has a tag number of 7, tag number 8, like that. So from this, how it takes PV1, because its function is take the data which has the tag number 1, take the data which has the tag number 2. What is the function of this? Take the data which has the tag number 3, take the data which has the tag number 4, and give the output. So everything is digital communication enabled devices are connected to this bus, that is DCS. That is DCS. DCS is an elephant. If you see in one part, it looks like wall. If you see another part, it looks like trunk, like that. So it is to get an overall idea about DCS. Why it is called DCS? If you see the conventional controller, how it is connected, controller output is connected to final control element. Final control element is connected to the process. Processor is connected to level transmitter. Level transmitter output is connected to controller. Like this, you need an arrangement, a sequence of arrangement must be correct. Then only it will work. But in the DCS, it is distributed. Here tag 1 is connected here. Tag 2 is connected here. Tag 3 is connected here. Tag 4 is connected here. Tag 5 is connected here. Tag 6 is connected here. It is not in sequence order. Distributed. That's why the hardwares are distributed. Software also may be distributed. So it is called, that's why as hardwares are distributed among the network, that's why it is called distributed control system. Distributed control system. The control is not controller are distributed. Hardwares are distributed across the network. That's why it is called DCS. Let us come to this diagram first again. Here, if we see, this is a controller. This is a controller. This is one controller. Here, you see that this level transmitter is not digital. Not digital. It is analog only. That's why this ADC controller has ADC. That's it receives that 420 milliamps and converts its data. Here we can say that this is combination of tag 1 and tag 3. Tag 1 access a level transmitter. Tag 3 is a controller. If you combine these two, this is controller. It receives 420 milliamps and places its data on the bus. That's all. It places its output on the bus. It places its data on the bus. Similarly, here, and the tag 2 and if you combine tag 2 and the tag 4, you see that the temperature is given to that ADC converts a network. So DCS directly handle smart devices, smart final control elements, as well as conventional controller also. So you need a suitable hardware to handle that. That's all. Here 420 milliamps. Here we are getting 420 milliamps. That's why you need this device. So anyhow, this device is connected to network, but you cannot connect this temperature transmitter to the network because since it works on analog only, so through the data is directly given to the controller. So what I shown here is further advanced. The final control element, temperature transmitter, everything is smart. So smart means it has a microcontroller based device, embedded system that itself will communicate through that communication medium, that bus. So so you can combine this operator station and LCU, local control unit. LCU means local control unit. It consists of one ADC, DAC, and it has computing power. If all this it has, then it is called local control unit. It acts as operator station also. If you see the difference between local control unit 1 and 2, the one has operator station also inside. It means the operator can interact with that. That is called operator station. Operator can interact. He can change the set point. So whatever he wants to do, he can do. The operator can operate through this operator station. But if you see the LCU2, local control unit 2, tag number 2, local control unit 2 or tag number 2, but it works as one of the hardwares with the tag number 2. It receives 420 milliamps from the temperature transmitter and calculates the controller output and gives out its value. It places both data on the bus. So it is not, because the thyristor power controller is not smart enough to receive digital data. That's why it directly gives that 420 milliamps here. So it doesn't mean that can we use analog devices along with the DC? Yes, that you can understand from this. There is no change at all in the left-hand side. Left-hand side, no change at all. Only right-hand side is changed. Right-hand side is changed. The field bus technology. The field bus technology, in that everything can be, already I have said, smart valve, already I have explained this. A smart valve can read the digital controller output and it will adjust the valve based on the digital data. Then it is called smart valve. Smart valve is connected to the field bus. Here, smart level transmitter. It places its data directly on the bus. A smart thyristor power controller. Smart thyristor power controller. The data, the field bus is directly giving its controller output in digital form. The smart thyristor power controller converted this into electric power. So here also a smart temperature. Smart means it has the ability to communicate through bus. That's all. So it directly places its data along with the tag number, so that that can be used anywhere in the bus. Anywhere in the bus. So that today, if here today the controller 1 is used to control level means tomorrow this can be assigned to some other controller. This can take care of that temperature process. That is very much possible without modifying the hardware structure, without modifying the hardware connections. We can change. Only thing is which tag value it has to look after. Which tag value it has to look after. Based on that, it will calculate. That's all. That's all. So there is no need to modify the hardware. We can do any modification through software. Any modification, whatever you want, you can do through software. That is very much possible if you use DCS. Therefore, it is very flexible. Modification is very much possible, very simple. If you change the software, then the program is modified. The program is modified. That is very much possible. The computer control networks, if you use PC as a controller, already I told you that if the PC fails, the entire system fails. Here also, you can notice that this is also on computer. This is also on computer. This is as a inside one microcontroller is there. This is also computer. It has computer. This is also has computer. This is also has computer. Computing power. Computer. And this is computer 1, computer 2, computer 3. So many computing devices are distributed, if this fails, what will happen? Heating element alone fails. But on the other hand, if it is direct digital control system, then that computer fails, the entire plant fails. The entire plant fails. That's why in the digital DCS system, if one computing device fails, there is no problem for the entire plant, but that particular loop alone affected. Particular loop alone affected. That is the advantage of digital controller. If you DDC, direct digital controller, if you go, the computer device fails, even though it has the ability to control all loops, we should not use like that, because if that fails, the entire plant fails. The entire plant fails. That is the drawback. The PC control, direct digital control, good for small process such as laboratory prototype or pilot plants, where the number of control loops is relatively small. In that case, you can use direct digital control or PC control. Another one is programmable logic control. What is the difference between programmable logic controller and DCS? Programmable logic controller is a subset of DCS, because DCS is superset. DCS is a superset. So any work that a programmable logic controller can do can also be done by DCS. Can also be done by DCS. That's why DCS is superset, PLC is a subset. What is PID controller? PID control loops, analog control loops, that is also subset of DCS. PLC also subset of DCS. So both can be done by using DCS. In DCS, you can do digital control also. On-off control you can do. By using on-off controller, we can use the program, we can implement the programmable logic control. All algorithms of PLCs can be implemented by using DCS. But nowadays, PLC, then what happened to PLC market? That will go down, To avoid that, what they are doing, they are implementing PID algorithm in the PLC. That's why we cannot say that nowadays PLCs will do only sequence of operations. They won't say, oh, our PLC will do all control algorithm also, like that they will tell. So they embed PID controllers inside the programmable logic controllers. But it never becomes DCS. It never becomes DCS. But it can control loop. PID controller and PLC can control loops, but it never becomes DCS. DCS is a superset. That many advantages are there. We'll see later. So, programmable logic control is a specialized process. What we have to do? Batch process is required in plant. That's why PLC overrides. In those days, what they will, I have to tell this, even though it is a programmable logic controller, I should tell, because I have to tell the ability of DCS that can do the work of PLC. So in a plant like Neyveli, they will shut down the thermal unit 1 is shut down this month. They will tell why. They will run for 3 months or 6 months continuously. Then they will shut down because they cannot run further. Because if any devices fails, the accident may happen. It is like bomb. We are talking about that Kudangulam, that is dangerous. No, nothing. Even NLC we have bombs. Huh? If the furnace blast, the entire NLC will gone. So it is all about control. It is all about control. So nothing is safe. Nothing is safe. At the same time, we engineers should not say that we should not do that. Otherwise, there is no power. There is no natural resources. There is no natural resources to use. We should use the other resources. That's why we should use with utmost care. That's all. So even thermal power station also dangerous. So and they do not know the consequence. The furnace, if you see, it will be about 7 floors height. The furnace, the entire college building, if you see as one building, it will be one furnace in NLC. It will be about 7 floors. You can go to 7th floor and you see that it is closed by a building. The furnace is closed by a building, not wall of buildings. Closed. You can see that furnace through window, because the inside furnace negative pressure is maintained. That's why flame will not come out through window. So the negative pressure gone, then the furnace gone. That's all. So negative pressure is maintained inside. That's why the flame will not come out. Because how to start that furnace? That's why I'm coming to that programmable logic controller. How in the NLC, how the furnaces are working? Pulverized lignite, not coal. Lignite means it is some 1 million years younger than coal. Another 1 million years required to convert this into coal. That much days, if it is inside that buried inside that ground, it will be converted into coal. But we cannot wait till then it becomes coal. That's why now itself we are using that. So pulverized lignite. So pulverized lignite, powder lignite will be pumped inside the furnace. It will burn to convert the water into steam. So to burn that, is it possible directly if you inject that pulverized powder inside and nothing will happen? Those days, my mothers used to use that stove used by wood stoves are they're using. Firewoods are used for that stove, and they know the technique how to start that. Initially, she will put camphor or some kerosene. She will put inside in a small bit of cow dung, dry cow dung. In that, she will put small amount of kerosene and ignite that. Then she will place that firewood above that. It starts ignited. The firewood will be ignited, then starts firing. So this is called startup sequence. Startup sequence. She only knows. And like that, we have to start that stove, firewood stove. So to start that, the sequence of operation is required. Once it is started, you can put more and more firewood. So like that, in the NLC also, once it is shut down, after 1 month, they will check all instruments, everything is okay. Then they will start again. That is called startup process. Shutdown also same type of sequence they have to do. They cannot, what we will do at home to turn on a pump, we'll switch off that pump. If you want to turn off a lamp, directly will turn off. Like that, you cannot do in a big power devices. Sequence of operation is required. That is done in sequence. For that, a programmable logic controller is used. First, what we have to do to start that furnace, initially the crude oil will be used to ignite that. So initially crude oil will be pumped inside. So it will be ignited. Once it is ignited, it develops temperature inside that furnace for some time. Then once a particular temperature is reached, then they will start injecting the pulverized lignite inside. They will close that crude oil. So it is sequence of operation. How much? Suppose it is not ignited, but if you continuously pump crude oil, what will happen? It will store inside. It will not be ignited. So then also some sequence is required. Whether it is flame got it or not, that we have to check. Like that, the sequence of operation has to be done. This valve has to be turned on, then this has to be turned on, then this has to be turned on, like that. The sequence of operation is there. For that, programmable logic controllers are required. So PLC is always used for batch process or sequence of operations, but DCS has the ability to do that. Instead of a PID controller, if you put a on-off controller, DCS will turn on. It is very simple for DCS. Give a logic 1 to turn on, logic 0 to turn off. Yeah, why not? It can do. So another LCU can be placed to turn on and off a particular device based on the input signals from the network. That is very much possible. That's why PLC is a subset of DCS. PLC is a subset of. If you put DCS, no need to have a PLC. No need to have a PLC. Or the PLC can become slave of that DCS. That is also possible. They used to give that facility also. Sir, our PLC can be interfaced with any DCS. They will tell. Then only we'll buy. So suppose already we have DCS. We implement on PLC there. That PLC can be interfaced with that DCS. That PLC can be interfaced with the DCS. So this PLC is monitored or controlled by the DCS. So see, DCS is a superset to do startup and shutdown continuous processes. Here the third point is, it is to do during startup and shutdown continuous processes. So shutdown also a sequence of operation. First thing, the steam pressure inside the vessel must be reduced. So for that we have to reduce the amount of heat. Amount of heat has to be reduced. The pressure inside has to be reduced. Gradually everything should be come to normal. Then we have to close that furnace. It should be a sequence of operation. Shutdown also. So it can be done by using DCS. So it is a most comprehensive DCS. You can do all PLC work also can be done by this. So it is a data highway bus. The data highway operator control panel is connected. Main control computer is connected. Supervisory host is connected to that main computer. Main computer connected to bus as well as supervisory control. Operator control panel. Archive data storage. If you want to store data, it is mandatory to store data of industry. All parameters has to be stored in a device, because if any accident happens, like black box in your pilot flight, this archive data has to be stored safe to analyze what happens to the plant, why that accident happens. Those analysis for that this old data is required. So local computer can be interfaced. Local computer is interfaced with the data highway. So this local computer interfaces with the process through data network. Here you cannot connect this to the internet, because it has separate protocol. This is meant for this industry only. So you need another interface that only knows this protocol and this protocol. Internet protocol, this interface device knows, then only you can. Otherwise, what will happen? The same internet protocol can be used to destroy this. That's why it is not allowed. Still, that's why it is proprietary standard, not international standard. They don't want to use international standard. If they use, if all international standards are used, this company knows that protocol means that he wants to spoil his business. Then what he will do? He will intrude into that network and he will do some disturbances. Hereafter this company DCS is not working fine, so we should not buy that, like that. No, so it is business. That's why they are not believing. That's why there is no one protocol for that industry. Many protocols are there because of safety only. If you use your own protocol, then others cannot intrude into that, and it is safe for the plant. Others cannot intrude in that. It is safe for the plant. That's all. We'll see one by one elements that are connected in the DCS, local control unit. Local control unit is nothing but embedded system. It has a microcontroller inside. It has the ability to interface with the communication ability. It has the communication ability with to interface with the bus. It has ADC, it has DC, DAC. That's all. You can use it as a PID controller. You can use it as a PLC. You can use it as if it is an on-off controller. Whatever may be you want to use, you can use as an advanced controller. You want to use it. Put an algorithm inside that local control unit. It works as an advanced controller. So the LCU is a general name. It consists of a MUSI. It has ADC. It has DAC. It has communication protocol, communication devices. So if you combine all these two together, then it is called LC, local control unit. It has one special address. For example, if you have you are buying one mobile, but it won't work, then you need a SIM. So that SIM is required to identified by that network. Your device is identified by that network. So your subscriber, your SIM is subscribed, then what it will do? It do the service. So whether you subscribed or not, once you put that SIM, it will identify one device is there, that network will, like that, it has the tag number. So it has a tag number. So this tag number is connected to that. So whatever its data, if it puts along with the tag number, it will place its data. Similar to your mobile system. What the messages comes in packets. One mobile is used in another town. It places its data as a packet with its number. So here, with the data, sent data, the data sent by which mobile, the data has to be received by another mobile. Both data are in the header. So based on that, your mobile takes the data from the bus. Whatever it doesn't give, your mobile selects the data, which data has to be taken, which data has to be ignored. Like that, it is taken. So the same way it is working. That's all. LCU is a local control unit. It has the ability to interface analog signal. It has the ability to give analog signal. It has the ability to communicate digitally, smart, and it has the ability to calculate. So these are the facilities it has, each local control unit. Data acquisition unit is a digital, discrete, and analog I/O can be handled. So if it has no this can be configured as a data acquisition unit, batch sequencing unit. So like PLC, it works. So local display unit. If you have a display is connected to this, a display unit is connected to this, and it becomes display unit. If you connect the keyboard input device, then it becomes a handheld unit, or human interface unit, HIA, human interface unit, like that. Bulk memory unit. If you want to store the processed data, then it is called bulk memory unit. So general purpose computer can be interfaced with that. Central operator display, data highway, local area network, LAN. So these two, this local area network is industrial network used here for this process side. On the other side, conventional unit will be used. Conventional protocol will be used. Internet protocol will be used on the other side. So this language cannot be, in that case, interface unit is required, which will convert this to that into this with the safe operation. That's all. The modes of computer control: manual, automatic, supervisory, advanced. These are all already we have seen. These are all already we have seen. Remote means we can change only set point to that controller which is connected. DCS systems are more flexible. Control algorithm can be changed and control configuration can be modified without having rewiring the system. No need to modify the wire. The wiring can be as such, but the control algorithm can be changed. Access large amount of current in the data highway. Monitoring trend of process condition. Any can be modified. Alternate among standard control strategies. Sightful engineer can use flexibility of this framework to implement the latest computer. So hardware is same. You can implement well and wish. So relay, switch, solenoid valve, motor drive. This can be interfaced. Digital generalized alphanumerical displays are possible. Any turbine flow meters can be interfaced. So this is not. This is also no need to explain. We'll go to that resolution and all, you know. If your number of bits increased, your resolution will increase. And the DCS vendor job is to install. Control engineer job is to configure. Built-in PID controller, how to tune PID controller and all there. These are all we skip. DCS vendors is mentioned here. First time. Another 15 minutes. So you can have a graphical window. So entire plant can be seen here. This is the plant unit 1. This is a distillation column. You can put a process status along with. You can easily visualize what happens inside. If your pressure increases here, you can change the color of this. You can change the color of this display so that any parameter goes beyond its normal value. The color can be changed here, so that you can understand easily. If you put this flow diagram is given, the process flow diagram is drawn here and the process variables are displayed here, then it will be convenient to understand what happens inside. So display is very advantageous in DCS. Another and the acknowledged alarm. Alarm means there are two types of alarm means there are two types. One is alarm without acknowledge. Another one is alarm with acknowledgement. Then alarm disenable. The first case is if any process variable goes beyond its normal value, then the alarm means it will blink in a different color. So this variable and a buzzer will be turned on. Suppose it is acknowledged means operator noticed that deviation means he will do something to quench that. So there is no need of that buzzer, only blinking required. So you can turn off that buzzer. If you acknowledge that I noticed, acknowledgement means I noticed, then immediately buzzer will turn off, but it will blink. And the color will be changed to orange. Red will be changed to orange. It will, but anyhow it blinks, so that variable is beyond. Once it becomes normal, again it becomes green. So like that, these are all very much possible to do, and graphical window definition is very much possible in the case of DCS. System. These are all local control unit. You know, this is local control unit number 100. Its controller output, how much process variable it receives. Everything can be displayed here with the trend display. Bar display. Trend display means like this. This is the trend display. So the process variables are displayed like this. So whatever way you want to display, that can be done with here in DCS because of computing ability. Any computers can be interfaced with your device. So that's why this is very much possible in the case of DCS. This is a trend display, trend window config. You can configure as you wish. As you wish. So here, if you want to magnify and see a particular area, the magnification button, data axis magnification button, y-axis magnification, x-axis magnification, reference. So many, the display trend can be modified. The operator can look at a particular point. Here you can notice that every data comes with a time tag. So these are all possible with the help of DCS. Instrument faceplate. One instrument is LCU acts as a PID controller. What the PID controller has set point, what is the process variable? Everything I want to see means you need not go to the field. You can bring that faceplate of that PID LCU acts, which acts as PID controller. That plate you can take and you can see the process variables as a bar chart as well as in the numerical value that you can see. So set value, what is the set value? What is the manipulated output? What is the process variable output? These are all you can see as instrument faceplate in a computer. There is no limitation for DCS. So, so you can use the faceplate of PID controller or any instrument. Faceplate can be seen, and the tuning can be done using signal flow can be done. Signal flow window, process alarm window, operator gate window, unit control window, trend window already we have seen, historical message report window. You can get the report also. So these are all many facilities that is available with the DCS. So let us. So here, even in keyboard, it is not a conventional keyboard. It has many functions and many LED displays. So it has operation mode selection, operator or engineer, depends. So operator cannot go beyond certain level like that. You can put the lock and all. These are all the possibilities that we can have control over that others. So why a network is not proprietary standard? Because of safety. Because if you know your protocol, others can intrude and they can give trouble. That's why many buses are there. Mod bus, Profi bus, HART protocol, foundation bus, field bus, foundation bus, Ethernet CAT, direct net, device net, control net, control common CC link, BSAP, Bristol BSAP, ASI, YSGP. So many networks are there because they don't want to use a standard protocol because of safety. Every company has their own protocol, but the idea is same. The idea behind the working principle behind all DCS is same, but protocol is different. Honeywell use their own protocol for the network because otherwise nowadays internet is very simple. Through internet they will intrude inside and they will give trouble to the plant. To avoid that, everyone is using their own internet networking protocol. Fisher Roseman has their own, Bailey their own, Yokogawa having their own, Force Marshal having their own, Siemens their own network, Foxborough they are having their own networking standards. If you have any questions, you can ask another Hold on. Another 8 minutes are there. If you have any questions, you can ask. If you don't want to ask, you can message me any question. I will not reveal your name. Maybe question may be silly, because silly questions make you clarity will be more. Any questions? So don't think that the question is silly. No question in the world is silly. It will give more light on the subject.
Professor,
So
there
if
is
you have any
a question from the chat box, Professor. Data question can help to analyze the IC engine testing parameters. Some Bharat from has asked some questions in chat box.
Yes, sir. Yes, sir. Actually, at the time of lecture itself, I answered that question.
Okay.
And so any data can be used for analysis, because yes, very much possible. There is no limitation number of data. You can acquire any number of data, depends upon number of channels that your ADC has. So you can analyze, no problem. Definitely, it's very much possible. Already I told, he asked earlier, half an hour back. That time itself I answered the question. Any other question? Okay.
Okay, thank you, Professor, for sparing your valuable time and given a very wonderful session on DCS. Actually, it is a very informative and highly useful session, Professor. Thank you very much.
Thank you. Thank you. Thank you. Thank you, Ananda. No question means shall I close?
Yes, yes, Professor, please.
Any question? Thank you. Thank you, Ananda.
Thank you, Professor. Thank you.
Very good.
Dear participants, next section start sharply at 11:30. Already resource person is here, and it is application of DCS in industries. Senior manager instrumentation from Shakti Sugars Limited is the resource person. So please be in time exactly at 11:30. Kindly join by 11:25. Thank you, and send the feedback for the first session. I will send the feedback link in the WhatsApp group. Thank you. 15 பேர் வந்திருக்காங்க. எல்லா அகாடமிக்ஸ்ல இருக்கிறாங்க. சர்டிஃபிகேட் வேணும் கூட அந்த காலேஜ்ல ஏதாவது வேலை நிறைய பார்த்துட்டு பண்றாங்க. கம்ப்ளீட்டா லீவா இருந்தா அதான் வந்துருவாங்க. ஃபுல்லா வந்து அதுக்கு தான் அதான் இதோட ப்ராப்ளம். டைரக்டா பிசிக்கலா வேலையே இருந்தாங்க பிரச்சனை இல்லை. நாம இது ஏன்னா ஒவ்வொரு செஷனும் நம்ம விசாரிச்சுட்டே இருக்கோம்.
அது சரி. ஏன்னா அப்புறம் அவங்களுக்கு நம்மளும் இருந்தோம்னா வேற ஒர்க் இருக்கும் போயிட்டு 10 நிமிஷம் பண்ணுவோம்.
நெட் ப்ராப்ளம், அதுல டேட்டா ப்ராப்ளம் ஃபுல்லே இருந்தாது. நிறைய டேட்டா அதனால அப்பப்போ அளவா வந்து போயிட்டு சார். குட் மார்னிங் சார். தேவையில்லைன்னு நினைக்கிறேன். அது எதுவும் சொல்லல. அவனே அனுப்பிச்சிடுவாங்க. போர்டு எக்ஸாம்ன்றதுனால அவனே சரிங்க. சார் உட்காருங்களா? நீங்க அப்படியே ஆரம்பிச்சிடுறீங்களா? அது வந்துருவாங்க சார். சார் 1 செகண்ட் சார். ஆன்ல தான் இருக்கும். சொல்லுங்க, நீங்க எல்லாம் பேசும்போது. இல்ல இல்லைங்க சார், மியூட் பண்ணிருக்க பாருங்க.
அப்ப உங்களுக்கு இப்ப வருதுங்களா செந்திலர் சார்? ஆடியபிள்
சார், 1 second சார். Very good morning to one and all present here. So it gives me pleasure in welcoming Mr. E.P. Vimalnathan, Senior Manager Instrumentation from Shakti Sugars Limited. He is the resource person for this session, that is application of DCS in industries, and I am very glad to introduce him. So he has completed his BE degree in the year 2006 at Government College of Engineering, Salem. And he has also obtained the boiler operation engineer certification, which is mandatory for boiler maintenance, issued by Director of Boilers, Chennai. He is also certified as an energy manager by the Bureau of Energy Efficiency, New Delhi. He has completed his PG ME in Applied Electronics in the year 2011 at AMS College, Namakkal. He is working as is joined in Shakti Sugars Limited in 1988, and he is having a vast experience of around 34 years in Shakti Sugars Limited, and he is the senior manager and head of the instrumentation department. He is also a life member of South Indian Sugarcane and the Sugar Technological Association, SISTA, and he has also published one paper during the annual convention of SISTA held at Vijayawada, Andhra Pradesh during the year 2011 and 2014 at Visakhapatnam on the role of automation and energy conservation respectively. So I am very glad to welcome Mr. Vimalnathan sir, and I hand over the session to Mr. Vimalnathan sir, please.
Thank you, Mr. President.
Sir, mic unmute. Sir, mic unmute. Sir, mic unmute.
Is it audible now?
Yes, sir. Yes, sir.
Thank you, Mr. Sendilar sir. Good morning to one and all present in this seminar. So he has introduced me. So we will directly go to the session, the distributed control system in an industrial environment. So if you go across any type or any sector of industries, there is sugar plant, power plant, or steel and paper, cement, oil and gas, whatever may be the industry, definitely you should heard about the PLC, DCS and SCADA. Because these automation technologies are now playing a very important role in all the industries, irrespective of industry sectors. So unless otherwise the industries are tapping these latest technology and automation, the industry cannot survive or industry cannot sustain in the market, because the market is consumer driven. So as a consumer, we also expect a good thing, a good product at very low cost. So this can be achieved only when we go with automation. So before going into the automation, we should know some basic things. That is what is things before move on to the DCS in depth. Yes, you are all well aware that the technique of making an apparatus or a process or a system to operate automatically without any manual intervention. Definition for an automation. Automation system in any industry and control. So we have to measure the process variable. So anything which can be measured can be controlled, and anything that can be controlled adds value to the business. This is the mantra of the automation system. So measurement and control. So these two is the basic thing required in any automation system. So whenever we measure the thing, we can control. So when we are able to control the things, definitely the profit will be increased, or the product quality will be increased. There is no doubt. So next, the role of automation, or everybody have in their own mind why to automate. So we have lot of person in India, lot of manpower is available. Then why should we go for automation? So generally it reduces the manpower, that everybody knows, but other things are very much important. It increases the throughput of each and individual equipments, and hence increases the productivity. So in an industry environment, we have number of pumps, fans, etc. So the all are to be controlled to utilize to the maximum possible extent. So this can be done only through the automation. So automation with the latest technology improves the productivity of the process by making performance and repetitive tasks faster. So this is very much important in batch type automation system. So the performance, and if we do the repetitive tasks, the human will get bored normally. But the automation system does not get bored, but all the time it gives same performance. This is the increased productivity with less labor automatically increases organization, that we are also know. But another important factor is it reduces the stress on the workforce and keeps workforce more happy, since anyone who has to do repetitive tasks over and again will get bored. So, but automation system do not get bored and runs at the same speed every time. A person, a skilled person, for one operator you take as an example, he is coming in night shift. So during this shift, his performance will be much lesser than the day shift. But if you put the automation system, it runs at the same speed every time. A happier workforce tends to be more productive because they are not stressed by their work, since system takes care. So the workforce is now free. So they are not stressed, means they will think of other things, improvement, the existing process, so that innovatively they can think and do. And cost will require, if the task required a high degree of accuracy. So if a machine requires very high degree of accuracy, definitely it cannot be run the day the manual. We must go for automation. So the next thing is, what are the parts of an automation system? There are only 3 parts. The sensor, the first, and controller. Sir, is it also audible to everybody, sir? Audible, sir?
Audible, sir.
Okay, sir. Thank you. So any parts of the automation system has three parts: sensor, controller, and final control element. So our DCS is the controller, DCS or PLC, whatever it may be, that is the comes under controller. The sensor produces 4 to 20 milliamps and it is fed to the DCS. The DCS does all the calculations and gives out output. If it is analog output in the form of 4 to 20 milliamps or it is digital output, it is on off. Then the final control elements will be valve or VFD or motor. That depends upon the parameter to be controlled. To take the sensor, it converts a physical quantity into an electrical quantity. So in an industrial environment, there are a lot of sensors. There's a pressure, temperature, flow, level, pH, conductivity, etc. So a lot of process variable sensed. So the figure in left side shows a mechanical gauge that is very old type of instrument. The right side is the smart instrument. So the disadvantage of mechanical gauge is it does not have any electrical output. So that remote control is, but used for local operations only. But this right side smart sensor, so that has the facility to gives out output in the form of 24 to 20 milliamps, irrespective of the process variable, that is whether it may be a pressure or temperature, to the controller, that may be PLC or DCS. So the controller, this is the main part here now. It receives the information from the sensor and generates the control output as per the software called as application program. So depending upon the process or equipment control philosophy, the software will be written and embedded or downloaded. That is called application program. Then the DCS generates audio visual alarm to alert the operation engineer in case of any abnormal condition. So the DCS is the heart of an automation system. It consists of CPU, central processing unit, memory, and I/O controllers, and communication subsystems also. So this is one of the DCS, how we are interconnecting. So generally the DCS, it is called a distributed control system. So why it is called a distributed control system? So earlier, in an earlier olden days, people are used to install all the sensor and the controller and final control element in one control room. So the size of the room was very bigger and troubleshooting if the problem was very much difficult because lot of wiring was there and also the pneumatic lines was there. So it was very difficult. So considering these problems, the people were thinking to distribute the control system across the geographical area so that now the sensor and final control elements will be at the field and the DCS will be in the control room. If the geographical area is bigger, for an example, if you take a oil and gas industry, that will be about 1 kilometer or 2 kilometer. The geographical geographical area will be very high. In that, one of the field control system DCS will be at maybe at field only. Then that will communicate either through the Profibus, field bus, or through wireless or through fiber optic. So this is now this mass flow meter, pressure transmitter, all through junction box it is connected to the mass link cabinet DCS, and this is the IO cabinet. This, if it is analog input, it will be handled by the analog input card. If it is digital input, it will be handled by the digital input card. Then, according to the control software, the output will be generated to control the particular loop. So there will be number of loops. For an example, generally the DCS will have more than 3,000, can handle up to 4,000 IOs, minimum 2,500 to 4,000 IOs, and even we can go up to 8,000 IOs, 10,000 IOs if we increase the process control unit and the processor capacity. And this is operator workstation where the controller, DCS controller will communicate with PC operator station. This is a minimum definition. This is one of the definition for DCS. DCS is a computation control system for a process or a plant, usually with many control loops in which autonomous controllers are distributed throughout the system. Then a distributed control system is a specially designed automated control system that consists of geographically distributed control elements over the plant or control area. So this is for in case of oil and gas industry, this definition would be applicable. If we take the history of DCS, in 1975, both US-based company Honeywell Automation company Yokogawa introduced their own product separately. So Honeywell introduced TDC 2000 model system. Yokogawa introduced Centum system. Now they have upgraded TDC 3000, then TPS total plant solution, then to upgraded continuously. Experian knowledge system. Now they have the latest DCS version. Yokogawa from Centum 1000, Centum 3000, Centum VP. So like that, they have also upgraded latest version, and depending upon the system, because operating system is being continuously upgraded from Windows 98, Windows NT, then Windows 7, Windows 8, 10, like that. So this is the general architecture of the DCS. Actually, one and there will be one engineering station and 3 to 4 operator station depending upon the plant size and capacity. And there will be number of field devices, mass flow meter, pressure, temperature, flow, the devices. Even PLC can be connected. Number of PLCs can be connected. And this is the bus, control bus, from where the operator system communicates. So this is the architecture of our power plant Honeywell system. So we have 4 number of operator stations. These are the operator station. So this is the engineering station. From engineering station, we can do all the set points. We can download the logic. We can do the graphics modification, etc. And these are the central control room locations. This is a field instrument for processor rack, HPM processor rack, which handles all analog input and output. And this is the digital compartment, DI/DO rack, which handles DI and DO input and outputs correspondingly. So this is actual architecture that is installed here. So these controllers, for example, this analog controller, for HPM, high performance manager. You see, HPM is a high performance manager. This LM is the logic manager. This is the Honeywell. If you go with some other thing, the controller will be different, but basic things will be same. The one field instead of HPM, they will tell the field control station like that. But all will be communicated through the Honeywell proprietary devices, and this is the NIM network interface local control station from where operator can monitor and control the plant. So this is one of the actual architecture of our DC. So this is in block diagram. It's a control. Controller means this is a operator station. This is a process 1 or process 2, process 3. Number of process will be there. Process means number of equipments connected to the network cable. From the network interface, it is communicating with the operator station. The components of the DCS. First is the engineering station. Is the process control or field control unit, and fourth is the communication system. So these 4 components forms the entire DCS system. So irrespective of the make of the DCS, the components will be same. The name may be little different, but 99% this should be the components for any DCS system all over the world. So this is our engineering station. Now we have upgraded our Honeywell system to the latest version of SubCon automation system. This is the engineering station from where we are doing all the logics. This is Dell make server grade, workstation grade PC, server PC. This engineering station. So the engineering station is the main station from where all the distributed controllers and the field devices, operator stations are configured. It is additionally used to configure a new controller, modifying the control logics, configure the smart field devices to create a new logics, to store the information, to create a new input or output point. So the engineering station is the important one, and from where all these operations are carried out. So this is next is the operator station or workstation, from where the operator can monitor the entire plant. So the operator can put any loop in auto, or he can take it in manual, and he will open the valve or close the valve. On seeing the alarms, he can take immediate remedial measures to sort out if there is any problem. And the IO capacity with single or dual monitors. Now the technology has improved. So instead of single monitor, dual monitors are available. So we can use any of them. That depends upon the requirement. So this photo shows our Honeywell DCS operator station. We can use this as an engineering station also by logging into our credentials. So all will be the graphical illustrations. So the entire plant equipment will be in the graphical form. So the operator can take or monitor each individual loops separately. If there is any problem, an audio visual alarm will come, so that operator will take immediate action to rectify the problem. The next is the process control unit, or it is also called a local control unit or local control station. So this station is situated in the control room or near to the field devices. That depends upon the geographical area, and all the field devices will be connected to it. In this station only, all the field devices are connected. This unit incorporates one or more distributed controllers. It contains CPU, I/O processor, I/O communication module, expansion module, etc. And all the field devices like sensor, actuator, connected to the I/O cards. If it is analog input, it is connected to the analog input field termination unit. If it is digital input, it will connect to the digital field termination unit. There will be a field termination unit, and all the I/O information, I/O signals from the field is connected. Hello. Hello. This unit. Hello, is it audible, sir?
Yes, sir.
Yes, sir. Audible, sir. Yes, sir.
Okay, sir. Okay. Station like set point, PID values, and other parameters, and also acquiring the information from the way. So in the CPU, in this process control, it analyzes all the inputs and process them based on the user program and sends the output signal via the corresponding output modules. If it is analog, this analog output module. If it is, so it can sense both analog and digital inputs and outputs. And these modules are extendable according to the number of inputs and outputs. So the next important thing is that this process control unit, CPU has the library function blocks in various logical operation functions and are not exclusive or exclusive. Now, the arithmetic operation block such as addition, subtraction, multiplication, division, and sequential control function blocks and communication function blocks to interface third-party devices through serial communication. So these are very much important to develop a logic. And also it includes PI control, that is proportional integral derivative control action, or proportional integral control, or proportional derivative control, split range control, etc. So this is have all the function block libraries, and during logic development, we will pick up the particular function blocks and connect it, link to develop a particular logic. So this is the component of our DCS system, old Honeywell system. This is HPM means high performance manager. It contains controller. This is I/O control card. This is total process controller. This is redundant. So I will come to the point next, redundant. This is LM controller. This is logic manager. So that is for to take care of digital input and outputs. This is for analog inputs and outputs. So this is another PLC type controller for used for our ash handling system. This is Siemens S7200 product family. This is the CPU. This is analog input, and this is digital input and digital output mode. So this is the DCS field termination cards of our Honeywell system. So this is for analog input and outputs. So this is from the field devices. These wires are coming from field transmitters. And after signal conditioning, the 4 to 20 milliamps will be converted into or 4 to 20 milliamps. That depends upon the model of the IO processor. Then from this, so what I have shown this, no, this controller. This is for digital input and outputs. So this, you see, this is 32 channel. So if the LED glows, the input is turned off. The input is. So this is the digital input and output modules of our Honeywell system. So this is the upgraded version of Subcon DC. We have modified this. We have upgraded since it is updated. We have installed about 18 years has gone. So we have upgraded. So this is the controller secondary, and this is the input controller, analog input and digital input, digital output controller. This is the field termination unit. These are the field, and from this prefab cable, it is connected here. This prefab cable, this is connected. Signal is going here. Next is the communication system. Next, DCS. The communication system is the most important part of the DCS, which is used to connect all the engineering, all the devices like engineering station, operator station, process control unit. So all are connected together for data transfer or to speak each node. So normally in this system, in our earlier version of Honeywell DCS, it was coaxial cable. Now it is Ethernet, that is FT, fault tolerant Ethernet cable. So the common protocol used in DCS communication are Ethernet. Generally we are used Ethernet. Profibus, Modbus, DeviceNet will from field to the controller only. The output of the DCS will go to the final control element, that is control valve or motorized valve or VFD, that is on-off valve. So this is the control valve. The control valve requires air for its operation. This is our feed water boiler, Thermax boiler, 85 tons capacity, 85 watt, 515 degrees centigrade boiler. It's feed water control valve. This is motorized valve. So this feed water control valve will receive 4 to 20 million signal to its positioner. Then the positioner opens and closes the valve. From this, from starter, whenever we switch open or close, we can close from the operator station, that is remotely from the control. As I have told already, we have upgraded our existing is ECS 700. So everybody has their own name. DCS capacity, generally DCS have the IO capacity, they will tell. Our DCS IO capacity is 3,000. This include digital output, all four. So these are the Cocoa India Limited, ABB Limited, Metso Automation, Emerson Process Management, Supinco Automation, Siemens, General Electric, Rockwell Automation. So these are the major DCS supplier all over the world. Now we will go deep into what exactly the DCS does in our power plant. Any power plant plays a very important role in realizing the following objective, that is monitoring, control, safety for plant and personnel, increased plant availability, longer equipment life. So the DCS plays an important role to realize these objectives. So the monitoring means regular monitoring, regular operations monitoring. That is, there will be number of control loops. For example, drum level, drum pressure, or furnace pressure. Like that, number of control loop will be there. So every loop will be put into auto mode. So the controller automatically maintains the set point set by the operation engineer. That is the regular operation. The management of disturbances. For an example, in a boiler, the drum level has to be maintained at 50% plus or minus 2% or 3% always. That is for normal RPs. So if there is any problem, so high or low, the alarm value above 60, if the drum level goes above 60%, alarm immediately will come. That is drum level high, alarm will come. If it goes 40%, low, alarm will come. So immediately engineer will monitor and do the necessary corrective actions. So this is another control action done by the DCS. Only is the regular next, the management of this, that is called management of disturbances. Then next is the handling of adverse events, that is the protection. For an example, if the drum level still goes beyond the control limit and it reaches 85 to 90%, immediately the boiler has to shut off. Or if the drum level goes below set value, below 20%, again the boiler has to shut off. So both the conditions are not desirable. It will have impact on operation of the plant. These three tasks are handled by the DCS. This already told. Another monitoring is for turbine speed. If turbine speed is very much important, since it equipment, the DCS monitors the speed of the turbine continuously. So if the turbine speed is 5,000, if the turbine speed goes above 5,500, immediately the turbine will trip. So overspeeding is not at all advisable. It is in danger to the plant and personnel. So the DCS takes this and vibration bearing temperatures also. If vibration goes high, immediately plant the turbine has to trip. So in the management of disturbances, one example is if the lube oil pressure goes low below the set point due to any reason, maybe oil maybe tripped, oil might have due to some other reason, another standby oil pump will start automatically. If any of the running feed pump trips, the standby feed pump will start automatically. So this is the functioning or management of disturbances. So the DCS takes care without manual intervention. So normally these conditions, in these conditions, disturbances cannot be operated, cannot be handled by manual operation. That is very difficult. So the adverse condition, as I have told, if it is turbine goes over speed, if the low by level low or vibration high, the turbine will get tripped. Plays a very important role in realizing the safety and availability. Very much necessary. So this is achieved by checking the critical parameters by 2x3 logic method. Generally, we called it as in an industrial environment, it's called 2x3 logic. So now you see this figure. So when A fails, the A may process, that is low boil pressure or over speed or flow low or pressure, temperature, whatever it may be. So when A fails, the plant gets tripped. This is one, it is called 1 out of 1 logic. In this, safety is low, availability is low. You please note that safety is very much important. At the same time, plant availability is equally important. For an example, you take power plant. So the power availability to us for the continuous 24 hours is very much desirable by us. So if the power fails 2 to thrice a day, then it is not desirable. So like that, the safety and availability both should be ensured for a power plant. So you see, this is the 1 out of 2 logic called when A or B fails, the plant trips. Please, this is only 1. This is 2. It is in AND logic. You see, fails. For an example, for one oil switches. So if it is connected in AND mode, AND logic. So if A or B fails, the plant A and B fails only, the plant will get through. In this, safety is high, but availability is low. Now you can see that 2 out of 3 logics. This is the logics we are using to availability of any plant. 2, 3 switches. It may be a pressure switch, temperature switch, that critical parameters production scheme. You see, when 2 out of 3 switches fails, the plant trips. That means if you are ensuring A and B or B and C, or that means we are ensuring there is a problem in the oil circuit. Definitely 100%. Then only the plant gets tripped. So these logics are realized by the DCS. So in this 2 out of 3 logics, the safety is also high and availability is high. Then we go for the redundancy in the DCS system. What do you mean by redundancy and why it is required? Since the DCS is the heart of the power plant operation control, plant trip due to single point failure is not desirable. Single point failure means if there is any problem in the power supply circuit of the processor, if the plant trips, that is lost to the power manufacturing company. In addition to the plant downtime, we have to incur a lakhs of rupees to restart the plant also. If you take the thermal plant of 200 to 10 megawatt, if plant trips and for restarting immediately, it will take minimum 3 to 4 hours. For our plant, it will take 2 hours. So it is waste. During that time, we have to feed the fuel. We have to use the extra fuel. But it does not think it will not do any output or product. Not desirable. Hence, most DC systems are designed with redundancy at power supply, CPU, and communication subsystem as a minimum. So this redundant configuration provided system reliability to a great extent, up to 99%. For that, the redundancy concept is being employed. So how redundancy is configured? So there will be a pair of redundant controller executes the same application. So the working one is called primary for data acquisition, process control, exchanging information on process control network. So called secondary processor that is used to and more of the working primary controller and real-time backup of the information needed by the controller. That means the secondary controller will always update the data. So in case if there is any problem, immediately the secondary controller will come into line within 50 milliseconds time. So that is called bumpless transfer. So that the planned operation cannot be affected and safety access of the system planned is also ensured because the secondary controller will take the control action within 50 milliseconds period. And the operation engineer will get an alarm. Then the maintenance instrument engineer will go and see and repair the failed one. And we can put in online also. So the following key features of the redundancy are automatic synchronization. That is called, so when primary fails, the secondary takes care. So before that, the secondary will update the database, sync, always in sync. Then real-time synchronization. That is every within below 50 milliseconds transfer, bumpless transfer. So the transfer will not affect any state of the outputs. If it is analog output or whatever digital output, the state will not be changed. So real-time mutual diagnosis, the both will speak on real-time basis. Online replacement. If there is any problem, we need not have to switch off the power supply. We can plug and play modules. We can replace online. The plant will not get affected. So this is the graphics as I have already told. The operator session will have the illustrations for the engineers. So this is the air and flue gas graphic picture, in you see this is the header pressure controller. It is in auto mode. You see it is in auto mode. So this is the set pressure. 1.4 is the output of the PID controller. 67.3%. Will be given to the cascade controller. From there it goes to the cold feeder. This cold feeder is controlled by the variable frequency drive, so that if the pressure goes low, the speed will increase to feed more cold. If the pressure goes high, the speed will decrease to feed less cold, so that the steam pressure at the steam header is maintained almost constant. So these graphical illustration also gives an indication that is in the form of color code. So if it is red, it is in off. If it is in green, it is in on condition, that is in operation. Like that, all other parameters such as this is the furnace temperature, 745 degrees centigrade. This is the furnace pressure, 0.4, and this is the pressure after boiler bank, like that. So this graphical illustration, on seeing this graphic space, the engineer can easily understand the operation of the boiler. So this is the turbine graphics. Here it shows this is the inlet pressure. So there will be one, if it is critical parameter, normally we provide 2 transmitters. So 81.4 is the turbine inlet pressure and 508 degree is the turbine inlet temperature. And this is the turbine chest pressure and the extraction, first extraction control valve, second extraction, this is the third extraction, like that. So everything will be representation. Apart from this, the plant parameters can be viewed. That is for boiler on total airflow, O2 percentage, furnace pressure. This is the important parameters of the boiler and turbines and electrical parameters. You see here the power generation, VAR, export power, frequency, power factor, 11 kV voltage, current, like that. This can be seen easily. There are 4 to 5 methods are there. One is the other is the function block diagram, FBD, then structured text, ST, SFC, then sequential. So now ladder logics or function block diagram is used in our plant. The ladder logic is nothing, it is originally developed to represent the relays and switch. We will see that. So it represents the whether switch is in or coil, like that. Then the function block diagram, and with a method to describe sequence of network rung operation, that so we have a function block for each and every equipment. For an example, motor control, valve control, like that. So if you take the motor control function block, it will have the input, it will have the output, it have the feedback signal, it have the emergency stop or production stop, like will be number of blocks properties will be there. That properties will be linked to make the our logics or to derive the logics as per the plant operations and requirement. Structured text, it is a text like C program that we are not using. Sequential function chart is a graphical programming language, but it is in a step-by-step format. But normally we use nowadays ladder logic also. For PLC, we are using ladder logic. But in DCS, we are using function block diagram. So this is the ladder logic program. So this is, we are deriving to start a motor. This is the stop push button. This is the trip contactor. This is the start push button. And this is the motor coil. Normally, this, if you take the hard wire, stop push button, emergency stop push button, you think of it, and this is the trip relay, OIL or over. If it is normal, this means NC. This is NO contact. So when these two are normal, if you press the start push button, they'll get energized and the motor runs. Once this, if you remove this start push button, this will be held by this contactor, auxiliary contacts. So during normal operation, this is the operation. If anything goes wrong, suppose if you press, if you wanted to stop, you press the stop push button, this is logic. So this is the our this is for auto. These are so whenever this auto selection is there, conveyor 2 feedback is coming. Path 1 is selected. This coil will get energized. Okay. So once this coil with energized, the path 1 is selected, this timer will get on. So like that, we are deriving the logic. This is for an example. I think everybody cannot understand because it is one page of the 10-page logic. For an example, if you wanted to operate one of the remote engagement solenoid valve, this is the command from DCS. Even though if you give command, this high pressure switch should be in off condition, and this solenoid valve should be in off. So then if you press give command from DCS, this will get on. Once this get on, this will get energized. This solenoid valve will get energized. So this is programming for the function block diagram. So this is PID, enhanced PID temperature control. So this is the temperature which is coming from the field. So this is the input field analog input card. This is connected PV. PV is nothing but the process variable. This PV engineering unit, PVE EU max means engineering unit maximum, engineering unit minimum, that is range 0 to 1200. Then set point program and high limit 0 to 250 or 1200. Like what that depends upon the individual loop characteristics. And the manual control, if this we can put in the manual mode or auto mode, that depend upon the operator or some auto program request also there. And we can set the PID, that is program proportional gain, integral gain, derivative gain, we can set. And this is the output. CVU calculated. This gives the output. This is the 4 to 20 milliamps comes, and this gives the output. That depends upon this, that speed of output variation will depend upon these PID values. So this is one of the function block diagram existing in our power plant. You see continuous blow down tank level control. This is the control valve. This is this PV is the tank level, that is LD0704. And this PID value, these values are PID values are set inside. If you double click in the programming mode, it will go to the PID values. That depends upon the set value, it does the output. Here they are telling MV. CV is calculated value, MV is the manipulated value. But this output, 4 to 20 milliamps output. Here also you see the SA fan motor VFD speed, that is going for control valve. This is going for control valve. This is for variable frequency drive speed reference. So that reference can be increase or decrease from this. This is another one type of function block. So this is the upgraded our Subcon DCS workstations. So earlier you have seen the Honeywell system I have shown you. Only 4 workstation was there, and 4 only more. Now here also the 4 workstation, but there is a dual monitors. So the 8 monitors are there, 8 displays are there. So that is the advantage of the technology. This is the new version. Nowadays, all these dual monitors, DCS systems are supplied by the dual monitor, so that the operator can see more or less all entire plant. So if you take, there will be 15 to 20 graphics display for a boiler. Boiler means air and flue gas, steam and water, and a turbine, swash, conveyors, coal handling, coal conveyor, bagasse conveyor, so that the operator, control room engineer will see more or less all the graphical system parameters at a time. That is the advantage of the dual monitor. So the reason why we are going to the dual monitor is this for this only. Okay, so I think we have come to an end. So if any question, any doubts, discuss, sir. Hello.
Hello, dear participants. If you have any queries, please ask.
No doubts.
Okay, thank you, sir. Actually, it seems there is everything is clear. So some chat box put the nice session. Thank you, sir. Right. So actually, during the COVID period, we unable to visit the industries, but you bring the lively the industrial scenario into every one of the system screen or mobile screens, sir. And thank you very much for the presentation and kindly sparing your valuable time. Thank you very much, sir.
Thank you. Thank you. Thank you, one and all. I take this opportunity to express my gratitude for the Senthil sir for having given this wonderful opportunity to participate in the webinar to share my experiences in the field of DCS. Thank you, sir. Thank you, everyone.
Thank you, sir. Dear participants, kindly share your feedback in the about this session. And the next session starts at exactly at 2 o'clock. The afternoon session will be Divine Yourself. That actually it is a IST compulsory session. So kindly be available to the session. And the Dr. Mrs. Subhashini from Head of the Department of Computer Application, also you doing PhD in yoga, she will be handle the session. So kindly join at 1:50 p.m. Thank you.